Welcome. Okay, the reason we use now a different Zoom channel is that I wanted to do some polls because yeah, the lectures behind the screen are not so interactive. And to get a bit of feedback, I thought it was nice to have some of your input. And Zoom does support a nice facility to do polls. I'm not sure if you did it before in one of the other lectures. So let's give it a try. I will now open the poll, and I hope that you now see two questions. This is just the test, so please answer them. And when the most questions are entered, then I will stop the poll. So I have now 14 answers out of 23. So still a few are missing. So the first question, does it work well? It works well, at least for the 14 persons that see the poll. And I see some persons do not see the poll. The question is, are you using the Zoom application, or are you using Zoom in a web browser? Maybe that is an issue. Okay, I see that most of the persons now found the poll. Yeah, it could be that in the web browser there is less functionality. So then, okay, this lecture you cannot participate in the polls. But if you have the Zoom app, it works well. Okay, I will now end the polling and you will see the results. I will share the results. And you see, okay, at least for the 17 persons able to see the poll, for them it worked well. I think for the others, about 6 that are on the web-based Zoom interface, they have no poll access, so that is good to know. And your age seems to be usually above 22. A few are 22 and nobody is below. Okay, let's now do a serious poll and see what you remember of the previous lecture. So here you see two questions, or now you should see two questions about the GIS and database architectures. Maybe you remember that last Monday I explained to you about the dual, the layered and the integrated architecture. So think hard. Which one do you need to remember and which one can you forget after you pass the exam on 25th of January? And the second question is about a simple feature. So we discussed the simple features from OGC and the complex features. Okay, I only have 10 responses. I would like to have at least 15. Okay, they are now being entered. 16. Okay, I end the poll. I will share you the results. I must say, I'm not that happy with your answers to question 1. And maybe that is showing that I did not explain it well on Monday, or that your memory is short, but actually the integrated architecture is the best architecture, and that is the one that is now being used most of the time. The dual and the layered architecture are a kind of solutions for situations where the database itself cannot support spatial functionality. So integrated architecture was the right answer. Only 5 people correct, and the others wrong. Luckily, the second question you did respond to a little better. or much better, I would say. A simple feature. Okay, yeah, a point is simple, but it is not the only type that is simple. Also a line, polyline and a polygon are simple features. A simple feature is self-contained. As you can see, the majority is correct here. And a simple feature is not referring to other simple features. That would make it a complex feature. So last poll before I really start with the lectures of today. It was about the second topic of last Monday and also the lab assignment about the valid polygons. You see now again 2 questions. And, please go ahead. I will give you 45 seconds to answer. So it's about the definition of polygons according to the Oxford Dictionary. And then the question, would a rectangle fit there or not? And the second question is looking at another definition of a polygon, actually from computational geometry. And is a self-intersecting polygon valid, or is that allowed? Okay, the seconds have passed. Okay, the majority of question 1 is, you said true, and I agree with you, but actually in the Oxford definition, there was a kind of note that the number of angles was usually more than 4. So this is a bit vague, but if you would interpret it as more than 4 angles, it is actually false. And so that is what I do not like about the Oxford Dictionary definition of a polygon. It kind of excludes the triangle and the rectangle. And I think these are also very clear polygons. Okay, the second question about computational geometry. Again, the majority is wrong. According to computational geometry, a polygon can indeed self-intersect. I don't think this is good, but okay, that is their definition. However, they made, if you remember well, a refined definition, and that is about the simple polygon, and that would exclude this self-intersecting. Okay, this is working well. Okay, here you see the results you obtained. And I'll now quit the polling. I will start sharing my screen for the lecture. And go to the first lecture about topology in GIS. And I'm quite sure you already have had some introduction to topology in the first quarter, in the introduction to GIS course. I will do a recapture of that, but also try to give you some mathematical definitions, and we'll give you some alternatives for that. Okay, this you should know, so I'll go over it rather quickly. So topology is the study of transformations and properties that are left invariant by the topological transformations. You could call that the rubber sheet transformations, and that are transformations that continuously deform the underlying space. And that includes, you can do a translate, a scale, and a rotate of the whole scene. And under these circumstances, the topological relationships do stay the same. They are important for databases because often topological relationships or predicates are used in queries. For example, select all cities located in a given area. a province, for example, and that located in, that is a topology relationship. The next example is select all municipalities adjacent to Amsterdam, and adjacent is a topological relationship. And the same in the third example, crossed by, which provinces are crossed by the River Rhine. And these are all database queries where you use predicates with the topological definitions. So this is for the topological relationships. Topology has this other side, as introduced also in the lecture Monday, that is the topology structure. And the topology structure, or a complex feature, is helping to do all kinds of analysis. For example, compute flow through a network, and then you know which connections are connected at nodes to which other connections. You can find neighbors of a certain area or a polygon. You can do overlay. So looking at just area features, here is a set of topology relationship. And so the first one is disjoint. It's a kind of funny thing to call this a relationship, but actually it is. The dark and the light gray areas are disjoint. Inside, touch, equal. You don't see them well, but okay, that's because they're exactly on top of each other. Cover, so one is covering completely the other. It's a bit similar to inside, but with cover, the two objects share a little bit of their boundary. So if we look over here, at this point over here, there's a shared boundary by the two objects. That is not happening with inside. And the last case is overlap. And more or less, these are the relationships you can have for 2D areas. Okay, what is wrong? These simple topological relationships were implemented differently by the different vendors of GIS systems and database systems, but in the same way that they had different rules for validation of a single polygon. So therefore, about 2 decades ago, 3 decades ago, a number of researchers tried to solve this by giving good definitions to topological relationships. And I will now cover 3 of them: the 4 intersection methods, or 4IM, dimension extended method, or DEM, or the calculus-based method, or CBM. So these will be now discussed in more detail. The 4 intersection method was introduced by Max Egenhofer. And yeah, it's a way to classify binary topological relationships, so between 2 objects. And let's first have in mind again 2 area objects. And let's call them X and Y. And let me switch my laser pointer to a pen. And I have the boundary and I have the interior. So this is my area, X. And the boundary is actually this red line over here. And the interior is everything else inside. So you have the object, let's call it X. You have the boundary, that is this thing, that is indicated with the symbol delta X. And we have the interior, that has the symbol, oops, X with the little O. Now I have this of 2 objects. I also have it of the other object Y, or also another object, y. Also the boundary and the interior. Let's put the label over here. So I have 4 sets, boundary x, interior x, and boundary y, interior y. And with these 4 sets, I do intersections. Boundary x intersected by the boundary y, boundary x intersected by the interior of y, boundary or interior of x and the boundary of y intersected, and both interiors intersected. In case of these 2 examples, it is all empty, the empty set. So I would have empty set 4 times. So sometimes indicated with this empty set symbol. So these 4 answers kind of indicate the type of relationship. So now let me make 2 different examples. I make a new x over here. And I make a new y. Let's do it with the same color, you will see it. Okay, I look at the boundaries of x and the boundary of y. Do they intersect? Yeah, they intersect over here and over here, so they intersect twice. And so this is not empty. So this is the empty symbol, and this little guy is the not empty. Boundary intersections is not empty. The boundary of x with the interior of y. The boundary of x, this is over here, and the interior of y, that's over here. So over here, this piece, let's make it fat, is also non-empty. It does exist. So again, I get a non-empty. Okay, reverse it. The interior of x with the boundary of y, is that empty or non-empty? No, the intersection is existing. It is actually this piece of the 2D space. So again, non-empty. Non-empty. And the last question, interior, again, non-empty. Look over here. So now in the second example, so this is reflecting to that situation, and this column is reflecting to this situation. So disjoint and overlap are now well defined. Let me do one more example to give you the feeling of how this works. This is my x. Over here I have the y object. Okay, same questions. The boundary of x intersecting with the boundary of y, true or false? No, it's not happening. So, okay, that one is empty. Then the boundary of x intersecting with the interior of y, here is the interior of y, here is the boundary of x, non-intersecting, again, empty. The third test, the interior of x intersecting with the boundary of y, yes, that is actually the case. So this is the interior of x, and it is intersecting with the boundary of y, actually what I now draw here in this fat line. So this is non-empty. And the last check I do is the interior of x with the interior of y, empty or non-empty. Of course, as you can see over here, completely non-empty. So the set exists. It is not an empty set. Okay, because I have now 4 sets that can either be empty or non-empty, like binary numbers, 0 or 1. In total, I can define 16 combinations. And here you see all the 16 combinations. And I did a number of them. I did the disjoint with the first example. I did the overlap, that was the last example. And I did an inside. That was this example. Inside can be tricky, or there is say a counterpart. Y can be inside X, or X can be inside Y. It's the same relation, but the role of the areas or the operands is different. So here you see, all combinations, but note in some combinations I do not have any topology relationship. And the reason that here in these cases that there is no topology relationship, this combination is impossible. Okay, look here. The boundaries are not intersecting. That is what this is saying. The boundary of X is not intersecting with the interior of Y. The boundary of Y is not intersecting with the interior of X, but the interiors are intersecting. So I have 2 areas where the interiors are somehow intersecting. Okay, let's draw it like this. But okay, this is not possible because now also at the boundary of the second object, Y, let's call this X, and let's call that second one Y, the boundary of Y is intersecting with the interior of X. So that means that the third column over here cannot be empty. And so this combination cannot be made. And not all 16 combinations are possible. That is what you see here and what you can also prove. So actually there are 6 real possibilities in the 4 intersection methods. Here they are depicted in an illustration. And yeah, 2 of the 6 cases are symmetric. That is the inside and that is the cover, by reversing the roles. For the others, it does not matter if you reverse the role. If you reverse X and Y, or as in this diagram, A1 and A2, relationship will stay the same. Okay, you can do the 4 intersection method not only for areas, area to area relationships, but also area to line, area to point, line to line, line to point, and point to point. And that will give you a quite large number of possible relationships. And they are very well defined. Because this empty, non-empty set, this point set theory from mathematics, is now giving very sharp definitions. There has been some extensions to this method, and one extension is called the 9 intersection method. And then the 2 objects do not only look at their interior and their boundary, but also at their exterior. And then you have kind of 9 combinations. Let's call this side the X object, and this the Y object. And you have the exterior, the boundary, and the interior. And you have the same for the body object. You have the exterior, you have the boundary, oops, and you have the interior. And in total, that will give you 9 different combinations, which are true or false. And this adds some expression power. You can distinguish a little bit more. What you also may have noted is, okay, an intersection like this, for example, the boundary-boundary intersection is now resulting in 2 points. But you could also have another situation, let's draw it like this over here, where you have a boundary-boundary intersection where the intersection is a line, and also over here again a point. And so instead of empty, non-empty, you can also be more, say, differentiating by, in case it is non-empty, looking at the dimension of the intersection. Is it a point? Is it a line? Or is the intersection maybe an area? Okay, and that idea is taken into account into the dimension extended method. And so again, we look at the 4 intersection methods, but now not only look empty, non-empty, but look at the dimension of the intersection. Empty, a point, a line, or an area. And because we have 4 sets, but for every set we have 4 options, in theory we could have 256 topological relationships. Okay, you should note that the dimension of the intersection must always be equal or lower than the lowest dimension of the operand. And what I mean is, if you look at the boundary of an area, the boundary is itself one-dimensional. The area is two-dimensional, but the boundary is one-dimensional. So if I intersect 2 one-dimensional operands, at most, the intersection can be one-dimensional. Or if I intersect an area object, say the interior of an area, with the boundary of another area, so that is a 2D intersected by a 1D operand, then at most the dimension of the intersection can be one-dimensional. Okay, this rules excludes a lot of cases. And if we now look at our 4 sets, and we are, okay, now not looking at area, but at area line relationships, you can say, looking at the dimension of the boundary of the area and the boundary of the line, that can at most be a 0-dimensional intersection, because the boundary of the line is so the boundary of a line is a point, the end point. So this is the line, and then the boundary is considered the endpoint here and the endpoint here. And an area, and the boundary of an area is, okay, the outer ring. That's the boundary. Okay, the intersection can at most be a point, and in this case, it is indeed a point. So it's a 0-dimensional primitive. So I only have 2 cases, either empty or it is a point, 0 dimension. Okay, now look at the other case. and the boundary of the area, again, this line, this ring, is the interior of the line. Okay, that is the interior. That itself is one-dimensional. So in theory, it can be either empty, zero-dimensional, or one-dimensional. If I would have a line like this, draw a second line for a while, and then the intersection of the interior of the line and the boundary of the area is indeed a one-dimensional primitive. Okay, and so on. And you analyze all the possibilities depending on the dimensions of the operands. And here you have 2, here you have 3, here you have 2, and here you have 2. That means in total 24 cases. Other cases are not possible. And by analyzing these again, these 24 cases, you see that many of them are possible. Look in the column where there is indicated the yes. Only a few no's are in the column. And it turns out that in total there are 17 cases possible. So with the dimension extended method, we can have 17 different relationships between a line and an area object. And note in this table, I did not write empty, non-empty, but I did write, okay, dash, meaning empty, or 0, the intersection is a point, or 1, the intersection is a line. Okay, and here you see all the 17 cases. The nice things of this classification is that any combination of a line and an area will fall in one of these 24 categories. So it is a complete classification. It's also exclusive. Any situation will only fall in one of these 24 categories. And so you only give one name to it. And okay, we looked at this category, line, area, 24 possible theoretically, in reality only 17 possible. And for area, there would also be 24 possible, but in reality only 9 are possible. Okay, 9 area. That's more than the 6 we had before. Remember, for the other methods, we had only 6 different cases. Now we have 9. What does it mean? That means that the dimension extended method is more expressive. And you can distinguish different relationships that you cannot distinguish with the 4 intersection methods. But it is still a lot, especially if you look at all the different primitives, the lines and the areas and the combinations. 52 types of topological relationships. It is quite hard as a human being to mention them. Okay, you can use the bit pattern, yes, no, or 0, 1, 2. And therefore, a last method was developed called the calculus-based method. And looking at the time, I think I will do that introduction of the calculus-based method after a short break. So I will stop sharing the screen, and I will also stop recording for a while, and see you back in 5 minutes. So 14:25, if there are no questions. Okay, welcome back, everybody. I saw that there was one question. Why not the part in the upper right? But I'm not sure which slide that was referring to. Andrenko, can you unmute and say to which slide I should go?
Yeah, hi. I think it was almost 4 slides before the last one.
Back or forward?
Backward.
Backward?
Yeah.
Backward?
You have drawn an example
Here?
with 2 polygons. I cannot see your screen.
Can you not see my screen?
No.
Then something is going wrong. Check what is going on. Share screen. Okay, it should now be better, I guess. Yeah.
Yes. But yeah, but now I cannot see the examples that you drawn before.
Yeah, I think they were removed by restarting the presentation. That's my mistake.
It was just a polygon with another polygon, and they had an intersection and the boundary, and you mentioned that it was a line and a point, but it was a part inside the second polygon, and I was wondering why we don't have also an intersection with an area.
Okay, this is area.
Yeah, something like that, yeah.
Yeah, that is called overlap. This is the overlap relation.
Mm-hmm.
And yeah, that does exist. So you can draw any combination of areas and you will fall in one of these 16 categories, at least in the 4 intersection methods. It will never fail. Somehow I feel I still not really understand your question correct, but maybe in the next break we continue via the chat.
Yeah, okay, thank you.
Okay, sorry for that. Okay, let's then go to the last methods, the calculus-based methods. These 52 relations are really a lot to remember, and the names are different, subtle, or the true, false. You cannot remember that as a human being. So in the calculus-based methods, there are again 2 operands, two geometries. Call them lambda 1 and lambda 2. And there's a relationship, and there can be 5 relationships: touch, in, cross, overlap, disjoint. And the operands, the lambdas, you can also still go to their boundaries or to their interiors, same as the 4 intersection methods. And here is a mathematical definition of the touch relationship. And so object 1 and object 2 are touching. And it can be area touching, or it can be line touching, or it can be a point and a line touching. Only not point-point, but this definition is valid for any type of object. And so we call it the touch, the relationship. If the intersection of the interiors is empty, but the intersection of the complete object, that means interior plus boundary, is non-empty. So, okay, if this is a line and interiors are not allowed to intersect, but if this, sorry, this is a second object, and this is a touch. And the in operation, and okay, the touch does also work for other combinations, like an area object and a line object, or This is also considered a touch. You don't have to touch in your boundary. Here you touch with the interior. So the interior intersection is empty. Okay, this is the interior of the line and this is the interior of the area, but their intersection is empty. But the intersection of the two objects is exactly at this point here where they touch. Okay, that is the formal definition of touch. Then a formal definition of in is that so object 1 is in object 2, that if you intersect object 1 and 2, then you get back object 1. So object 1 is in object 2. And so if I intersect them, then yeah, I get back this object, and that is their intersection. But there is another condition, and the interior intersection should not be empty. And this is valid for every situation. That means point, 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 line, point area, line, line, line area, area, area. All the 6 possible primitives that you can combine. There is a cross, and this is a bit more tricky definition. Looks also at the dimension of the intersection of the interiors, and it tests if it is equal to the maximum of the dimension of the interior of the first object and the dimension of the second object minus 1. And so cross is typically something like this. Okay, what does it mean? The interior intersection is this point. So the dimension of this intersection is 0. It's a 0-dimensional intersection. The dimension of the interior of the first one is everything except the endpoint. That's a complete line, so the dimension is 1. Dimension of the interior of the second line is again a line except the endpoints. So it's the dimension of a line is again 1. So the maximum of 1 and 1 is 1, and I subtract that minus 1. So over here I end up with 0, and that is also the dimension of both the left and the right side. So this is correct. Okay, what would be not correct? If I would have an intersection like this, because then the dimension of the intersection is 1. So then this side I would have 1, and on this side I would still have 0. Also for this example, and it is better to use different colors. And there are some more conditions. The intersecting of the two objects does not result in either of the objects. So the intersection of two objects here gives back the first object in case of inside. So that should not be the case, or it should also not be the other object. For example, second object inside the other object. And this is defined only for line, line, and line area objects. The last two definitions, overlap. So we have, let's draw an example. Okay, you could say, is there perhaps a cross over here? Let's go back to this slide and let's try to have another color and check if this would be a cross, because it looks a bit like this guy over here. So is this a cross? Let's have a look. The intersection of the interiors, okay, that is over here. That dimension is 1. Okay, so we have a 1 over here. the dimension of the interior of the first object, that's the line, that is 1. And the dimension of the second object, that is the area is 2. So the maximum of 1 and 2 is 1. I subtract with 1 and I get then 0. So you see this condition is now not fulfilled for this example. And so it cannot be a cross. And therefore, it looks a bit like a cross, but it is not a cross. So let's have a look at this case over here. Maybe it's an overlap. The dimension of the first object, the interior, is 1. Should be equal to the dimension of the second object. No, that is not true. But okay, look here. Also, this is not valid. We may not apply this operation for line area objects. So okay, we have to make this an area object like this. Interiors equal, yeah. Intersection of interiors, yeah, that is also equal. So this is 2-dimensional, 2-dimensional, 2-dimensional. And then intersecting both objects will not result in giving the first object back, nor will it result in giving you the second object back. So that is called overlap. But still, okay, what is then this type of situation? It is not a touch, because the interiors intersection is empty. It is not an inside. So did I make a mistake here? No, I did not make a mistake. So it is still unclear. And certainly not a disjoint, because that means there is no overlap at all in the two objects. Okay.
Hello.
Yeah.
Sorry, I have a question about the cross again. Can you go back to that slide?
Yeah.
There in the definition, it says the maximum dimension of the first object, the interior, and the second one. But if we cross a line, so the interior would be dimension 1, right?
Yeah.
And the interior dimension of the polygon would be 2.
2, right? Yeah.
So if we take the maximum of that, that's 2 minus 1. So
sorry. Yeah, you were right. Thanks for the correction. The maximum of 1 and 2 is of course 2.
So the result would be not 0. So
yeah, it is 1. Yeah.
It is a valid cross, right?
No, it is a cross. So thanks for the help. I was getting worried that I would not have an answer for this situation, but you're right. We take the minimum between 1 and 2, and as clearly showing that I should take the maximum. Thanks for your help.
Yeah, and then can you just explain maybe in one sentence again what the difference in between the cross and the overlap is? Because I'm still a little bit confused by that.
Yeah, it is best to look at examples. So let me go to this slide that is a bit less, or to this one. So I would call this a cross, and I would call, say, this an overlap in the intersection. And yeah, is it so important to make this distinction? It is rather specific, and it is indeed this distinction between the dimension of the intersections of the interiors and the individual dimensions. And so somehow, yeah,
Yeah, I think I get the difference.
would this be cross or overlap? I think this is also an overlap. But all these operations can be put in this is the decision tree, where you go with your object to the top of the tree. Look at the interiors. Is the intersection of the interiors empty? No, it is not empty. So this is false. I forgot about this part. Then I look at when I intersect the two objects, do I get back the first object? No, it's not an insight. But do I get back the second object? No, it's also not the second object. And okay, would this be a cross or an overlap? The interior intersection is this complete area, so it's 2D. So we have 2D on this side. This is 2D, interior of the first one. This is 2D, the first one, or the second one. So the maximum of 2 and 2 is 2, minus 1 is 1. So it is false. So true, false all the time. So it is false. So that classifies as an overlap. And so this is overlap according to the calculus-based methods. And yeah, we have the example with the line touching or overlapping. So the difference is quite subtle between cross and overlap. That is fully admitted.
Okay, thank you very much.
Okay. Until now, I just discussed 2D cases, but in reality, of course, we also have 3D geometries. Instead of points, lines, and area, we also have volumes. Discussed a little bit Monday. And also this calculus-based methods, the definitions given here on this slide and this slide, work without any adaptation. So you also then have in 3D topology relationships well defined. More extensions have been made by various researchers. The 9 intersection methods, looking at not only the boundary and the interior, also the exterior. I already explained that. Then you get 3 times 3 intersections is 9 intersections, S1 until S9, giving, in theory, 2 to the power 9 options. Really a lot, 512. People also have been trying to do topology relationships for fuzzy objects. For example, one way to characterize a fuzzy area is having a kernel area, and here you are in the kernel 100% sure and that the object is lying. In the outside here, you are 100% sure that is not the location of that area object, but in the intermediate zone, it is unsure. And you can imagine that if you have 2 of these unsure or fuzzy objects, that you can make a more refined relationship. For example, the sure part of the first one does intersect with the unsure part of the second one, but not with the sure part. That is different, that it does intersect the sure part of the first one with the sure part of the second one. That is for sure an intersection. But the unsure intersection is even better than unsure intersection. Then still it could intersect, but it gets less likely. Okay, you can get the picture a little bit, I hope, with fuzzy objects that you can also refine their topological relationships. And we can also look at the temporal dimensions of moving objects. Do they relate somehow? Do their trajectories intersect or not? I will not go in these details now. I will do one more poll at the end of this part. And I will launch the polls. And you should be able to see the polls. And there are, as before, 2 questions. The first one is about 4 intersection methods. Does it also work in 3D? Think hard. Could it work in 3D? Okay, I only see one answer. Please, others think. Okay, they are not easy questions. And I did not discuss this 3D aspect in the relation of the 4 intersection methods. And the second question is about the rubber sheet transformation. Does it have an influence on the topological relationships or on the topology structure, the complex features, or none of the above? Okay, 13 answers by now. 5, 3, 4, 3, 2, 1, 0. I now end the poll and I will share with you the results. The 4 intersection method. Could you use that approach also in 3D? And the actual answer is yes. You can use that, the same set of definitions in 3D. And so you kind of thought maybe the 9 intersection method is needed. Also, the 9 intersection method works in 3D, but it also works in 2D. And the same is true for the 4 intersection methods and for the calculus-based method. So the second answer was correct. Yes, it does work already. Second question, rubber sheet transformation, does it change topological relationships or topological structure? Yes or no? And the right answer is none of the above. So both the relationships are not changed when you are doing rubber sheeting, and also the structure. So think about the road network or the planar partition. We are doing rubber sheeting. The connections stay the same. The neighbor relations stay the same. So that does not have any influence. Okay, it's good to see that now the majority had the right answer. Let's have another 5-minute break. So see you back at 14:53. So 5 minutes from now, and then we continue with the constraint parts. Okay, I see in the chat one question about what does the symbol mean, the head symbol. Actually, it was not the head symbol, but it was the not symbol. And the not symbol is a little horizontal line followed by a little vertical line. It means not. So you have empty, and that is the circle with a diagonal dash through it. That means the empty set. And not empty set is, okay, this little symbol followed by the empty set. That is the not empty.
I also have a question.
Yeah, please go ahead.
So it's actually about your previous lecture, and it was about the direction of the of a polygon. You note the how do you say, the corners. So when I was doing the assignment, and you write polygons to WKT, BKTA.
Yeah.
Sorry. Yeah. So when you write them, I don't know which, because when I looked online, one source would do clockwise and the other source would do counterclockwise. So I was confused which order I should take.
Yeah, Daniel, the confusion is correct. Different standards have different conventions, and In the Netherlands, we had a guideline that we preferred clockwise orientation for polygons. So, yeah, okay, that's what we assumed in the Netherlands. But after some discussions in ISO, they decided that counterclockwise is the correct orientation of a polygon. And okay, some systems do check it, for example, Oracle, and some other systems do not care about the orientation. They say, okay, you may draw it in any direction, clockwise, counterclockwise, I don't mind as a system. But okay, if you have to answer the question without any context, what is a valid polygon? Is it drawn clockwise or counterclockwise? Then the answer should be counterclockwise, because that is what ISO has in its definition, and somehow ISO is the highest in the authority.
All right, so when you do it in PSQL, then you do the first polygon, which is the outer polygon, counterclockwise, and the second one, for instance, if you would do an inner polygon,
Yeah.
you would do clockwise.
Exactly. So the inner rings are in the opposite orientation. Correct.
Right. Okay. Good. That
Correct, Daniel.
Thank you.
Okay. See you all in 3 minutes now. Okay, welcome back. It was a mini break, but we still have a lot to cover. I will not do the lecturing now, but I will do first the polling. And so the next topic in the lecture will be constraints. And I will not tell you what constraints are. I will first ask you some questions about it. So it's very hard. And at the end of the lecture, I will do the same poll again. And so I say constraints are only useful in geographic applications. Yeah, yes, because you are using simple features. No, you can also use constraints in other non-spatial applications. And the second question is, okay, current technology does well support constraints in the implementation. Yeah, well, very well, because SQL 92 has in the standard defined the assertion. No, it's not at all possible with the technology of today. Or, yeah, it is somewhat possible. Okay, these are the options. I'm counting down. 5, 4, 3, 2, 1. Okay. Now the poll is ended. I will share the results. And here you see the answers. Okay, I will tell you, you are correct in most of the cases. So this shows that maybe I can better tell nothing and pose the questions, or the questions are too easy in this case, because it is true constraints are not only important in geographic applications, but also in other kinds of applications. And the implementation, yeah. It is not black-white. It's not very well supported, but you can also not claim it is not supported at all. There are some options, as you will see. Okay, let's go to the lecture. Sorry. You don't see what I see, but I don't see what I want to see. Let's share again. Last attempt. Something is going funny with the screen sharing. Okay, now maybe that it was a black screen from the end. Okay, I hope you can now see the start screen of the constraint lecture. Please shout if not the case. Okay, this is about constraints in geographic information models, but as was already clear in the poll, actually this is also very valuable in all kinds of other systems, information systems. It's a bit special topic because after a short introduction, I will go into 3 applications, geographic applications, data sets where constraints are important. And there are different types of constraints. So after these 3 applications, I will try to classify the different types of constraints. And in the second part of the lecture on constraints, I will look at, okay, how is it possible to implement them? What is the support in the database and or other systems to support constraints in implementation? And what is a good methodology to create constraints, to define them, to specify them? I'm afraid it will be difficult to stay in time, but I will try to do my best. Okay, in the first lecture of the course, Wilco introduced you to UML modeling, Unified Modeling Language, and that is actually from the object management group, and they have a kind of philosophy of the model-driven architecture. So you develop systems based on the model. It's the foundation for the system development. And one of the most important types of diagrams, way of modeling, was the class diagram, where you have the names of a class, the attributes, the name of an attribute, the type of an attribute, possibly the operation, and also very much the associations. And there were special cases like the generalization is a, or the aggregation part of. And Wilco did not discuss so much the constraints, but they are very important. And here you see a UML diagram with the classes, the class names, the attributes, attribute names, the associations, different types. You see over here the generalization or is a. Let me see if I can find the aggregation. Yeah, here you see, for example, the aggregation with the diamond heads, and the others are normal associations. This is another aggregation. And here you see a class with also an operation. Here also an operation. And so this is a typical UML class diagram, as you will find many, not only in geographic information, but in many applications. Okay, so what are constraints and why do I want to talk about them? Constraints are conditions which always have to be fulfilled by the user and or data processing operator of the system. And constraints can be related to the property of an object or to a relation between two objects. And to give a simple example, a tree should never stand in the water, it should always stand on the land. Or perhaps another example is a house or a building should be connected to the air surface. It should not float in the air or be below the surface. Then I would not call it a house, especially if it is floating in the air. I would call it a helicopter or an airplane, but not a house anymore. And having these constraints, the house is connected to the Earth's surface, or a tree should not stand in the water. That helps me. Why? It adds meaning. It adds semantic to the model, to the UML model. And when I specify the constraint explicitly, I can check. When somebody is entering new data, or when I receive a data set, I can ask by the machine, does it fulfill all the constraints? Or in other words, is it meaningful data or is it nonsense? And constraints should be modeled once in the UML model, but you can use it in different components of the system. For example, when you are editing in a GIS or a CAD environment and you are creating new objects or changing objects, you could check if the constraints are fulfilled. For me, very important is when you store the objects, then I really want to be sure that the constraints are fulfilled, because maybe during editing for some time you may have invalid, say, situations, and you are not ready with the edit operation. And also when you exchange data, for example, over the internet, you have an encoding, for example, in XML, and then you should also use the constraints, and also the sender and receiver should agree on the same constraints. Okay, example one, landscape design, virtual reality system. And we had some colleagues in Wageningen University. You know, they are doing all kinds of agricultural and environmental studies. They have developed their own system called Salix2 to support the landscape architects in their designs. And they can sketch the plantation of trees, bushes, different types of ground surfaces. And the system also supports the growing, so the aging of the trees, that they get bigger and bigger. But they were bothered themselves that some architects could make very strange designs and that were not really possible. And they asked us in Delft as engineers, can we not improve the system by implementing constraints? And that was the master thesis project of Yilda Lausma. She was a geomatics student a couple of years ago, and she did investigate this situation. And the idea is that the constraint should help the designer to make better valid landscape designs. So this is the user interface. For orientation, you have a little guy here, a person called Dilbert, showing you a little bit of the scale. And you have different types of bushes and trees. And you can put them at certain locations via the user interface. And this is an overview of the class diagram of this system, Salix tool. For the ground objects, so that is the Earth surface, there are a number of options. It can be water, it can be pavement, it can be grass, or it can be a bridge. And that is what you can have as surface. Then on top of that, you can have trees and bushes. Okay, two types of trees, the Frax X and the Q-Rub, and three types of bushes. And okay, these three classes are, say, the foundation of this information system. Okay, this is the scheme. Where do we find these classes? First, we have a digital elevation model, so to represent the Earth's surface. We have the plantation layout that is consisting of the ground surface objects, either water, pavement, grass, or bridges. Look here, there's the generalization class. So really try to read the UML diagrams. What does it mean? For now, ignore the colored lines. Just look at the black lines. And in addition to the plantation layout with the ground surface, we have the plantation objects. And there are two kinds of specializations, the tree and the bush. And the tree has two types, and the bush has three subtypes. Okay, now have a look at the colored lines. For example, this one over here, and maybe when I zoom in, you can see it a little bit better. So I have a tree and a bush, and one of the design rules from landscape architect is that in Europe, they would like to have the bushes south of the tree. Otherwise, the bushes get no sunlight and they do not grow. And here you see many more. For example, the distance of this tree, the Q-Rub, to the pavement can be less than half a meter. Or the distance between two of these trees should be more than 8 meters. So all these kinds of constraints have been added with these colored lines, and they are here phrased in text, and also color-coded about the different categories. So you have a direction, at the bush always to the south of the tree. You have topology. The bush is always disjoint or meets the water. The bush always has to meet or be disjoint to paved areas. Metric, where you include some kind of distance in your constraint. Can be temporal constraints, how long a certain tree can live. A quantity, you can specify in this area there must be at least 10 trees. Thematic, where you look at the type of the ground surface. And so it's paved area, it is not water or grass. And you can make combinations. And you can combine them always with and. So remember that in constraints, you always see the ends between the individual constraints. And if you combine them with an and, you can say you get a new constraint, a complex constraint. How to specify them? Okay, I added them to the nice picture, but you can always try to express them more formally in SQL. So remember, the UML class diagram can also be converted to SQL by create table statements. And the relations are there via the foreign key, primary key, and the joins. But in addition to the create table, and you have these others here, like the create index, there's also the create assertion. An assertion, you give a name, and then you have the keyword check, and then you specify what to check. So I want to now specify formally in the SQL 92 standard, a bush never lies inside the water. So I say create assertion, it's my first constraint, and I check. And now here, the body of the constraint is actually an SQL query. It should not exist that when I select from both the table with the trees and the table with the ground objects, where the tree type is one of these three types, and the type of the ground polygon is water, and there is this inside relation between the ground and the tree location, and that must be valid or true. I may not find these combinations of trees standing in the water. This is the SQL speak of this statement. However, and as you can see in the red, this is not implemented in mainstream databases, not in Oracle, not in Postgres, not in Informix, not in MySQL, really. And it will be very useful, but it's not there. We have to live with it. So what we can do is create what is called in Oracle triggers and procedures. So this is the trigger. So we create a trigger, and we can give it a name. And this is the definition of the trigger. And the trigger is happening when we do an insert in this table, the table with the trees. And okay, this is the body. If then the tree is of this type, then I say we report it's a bush, and we call this function the actual check. If it's another type, we say, okay, we don't have to check this constraint, but okay, if it's a kind of bush object, we want to do this check. A bush is never placed inside the water because that is the constraint we are checking. And here is the SQL code for the procedure. And the procedure is this PR topology check one, procedure for topology check one. Exactly the same as over here. This is the name, and here is the definition of this procedure. And over here, after a number of declarations of the types, you see the actual SQL statement that is doing again this is kind of query with the geometry of the ground elements and the geometry of the bushes, where there has to be a interaction, and so it is really quite relaxed. It can be touch, it can be overlap, it can be inside, only not disjoint. So that is what any interact is meaning. And this is the one way of how Oracle can specify topology relationships. Okay, and then in the end, the error is erased. And that means if you try to do this with an insert statement and put such a bush in a location where there is water, your transaction will not be committed, and you get an error message and it fails. It does not happen. For example, if you would put it over here in the water somewhere, and you put two trees over here, and that is a wrong location. Okay, and that is That should never happen. Okay, well, what did we learn from this application? First, constraints occur at many different places. Mainly, we encounter them in the user interface, where the person is designing a landscape architect, and we want to avoid mistakes. But it also happened in the data storage, where we implemented it with the procedures and the triggers and procedures. When we decoupled the database and the user interface too much, then the designer could do a lot of false designs and only get at the end, when he tries to commit or insert his edits in the database, he gets a warning. And so it's important to give direct warnings, and that means, okay, whenever some edits have been done, you should give feedback rather quickly, or do the insert quick and not wait till the end of the session. Yeah, I was really expecting that the databases would support assertions because they were part of the SQL standard. That was not true, so that was a disappointment. And this was quite some years ago, but I checked again recently, and it is still not implemented. What was funny in this example, it was not only a geographic or spatial application, it also had some clear temporal dimension by the growing of the plantation of the trees and the bushes. So you can now do an initial plantation that is correct, but after 5 years or 10 years of growing, it may give you a conflict. For example, trees getting too close because they are growing towards each other. You can evaluate that. Okay, given the time, I will now fast forward through the other applications. You can see them in the lecture notes and also in the papers on Brightspace. There is more detailed explanation of these applications. I will go to now to point 6, the support of constraints. So I'll do a super fast forward. So now we are here. By the way, if things were unclear during the fast forward, put a question in the discussion board on Brightspace. I will check that and respond. If you have time now, you can also put it in the chat now or next week. Next week, Monday, we have another lecture. Okay, let's have a quick look before concluding at the support of constraints in systems, databases, and others. UML, Unified Modeling Language. Actually, it is quite well supported over there. They have, in addition to the diagrams, such as the class diagram and other diagrams, they have also a language called Object Constraint Language, or OCL. It has 4 types of constraints, and we will mainly look now at the first one, the invariant, a condition that is always true before an operation, after the operation. There are other constraints. For example, one is checking before an operation only. The other one is checking after an operation. And a guard is used as a constraint in an state diagram, which is another type of diagram than the class diagram. UML is a formal language, so not natural text. It is well specified. And I will give you an example. It first starts with a context, as it is called in OCL, and that means, okay, to which class does it apply? For example, there could be a rule that you cannot have very small parcels, and the area should be at least 5 square meters. Then the context is parcel, or perceel in Dutch. Then the actual constraint is specified, and in this case it's an invariant, so inv, and the name is what I give it, a minimal area or a minimaal oppervlak. That's just a name. It could also be called Peter, this constraint, or constraint 1, or January, whatever you want. This is just a name. It should be unique. And then the second line is the actual constraint. And that states, okay, self, referring to parcel, dot oppervlakte area should be larger than 5. Another example, again to the parcel, so the context is parcel, and the name of the constraint is has owner, and there's an association from parcel to owners, and that association should not be empty. And what I really wish is that I could translate this very nice OCL into the DDL, data definition language, for the database implementation, the database schema, or when I exchange data in the XML schema of a document that is being exchanged, or when I edit in the user interface, the user interface thus understands these constraints, because if I then start drawing a very small parcel, I will get a warning from the editor, because it's part of the edit rules. Okay, not so. There's not support at database level, also at the editor, it is not so well supported. Okay, but what is there? The standard has domain constraints, and these are things like the type. Is it an enumeration type? Is it a range type? That is supported and it works well. So I will not discuss this further. General constraints, assertions, as said, they would allow you to really encode any constraint, but they are not supported at all. The third category, which is supported in part, is the base table constraint. So that's a constraint related to a table. So these are the first category, the assertions. These are SQL statements like the create table or the create index or the select. And you see how elegant you can specify certain constraints. The first one is check that the tree is not higher than 10 units. Sometimes you can specify the same constraint in two ways. So example 1a and 1b are the same. So in 1a I said, okay, check if the height of the tree is less than 10 meters. And then in example 1b I say, okay, check if there does not exist a tree which is higher than 10 meters. And so they are doing the same, but specified differently. Okay, with assertions, you can not only look at one table, like the table with the trees, but you can also look at combinations. The tree may not stand in the water. We already kind of saw that example. Here it is in a bit of easier syntax than the Oracle syntax. It should not exist that when I select from the tree and the water table that I can find any tree in any piece of water area. Okay, they are very powerful. You can specify anything, thematic, you can specify the text, numbers, time, geometry, but okay, not implemented. Okay, what is implemented? Base table constraints, but I said in part. And why? Because in theory, base table constraints are equivalent to assertions. And here you see the example of that the tree should not stand in the water as a base table constraint. So here I have the create table statement for the tree. It has an identifier, it has a height, it has a location of a different type. But I also attach at the same level where I specify the attributes, I specify the constraint. And the constraints for this table is called tree not in water. And then the keyword check, and then a bit of SQL code. And then I specify, okay, it should not exist that I can find a tree in the water. The database does not support a base table constraint with a subselect. So this part over here, where I have a select in the check, part of the base table constraint, that is not allowed. Okay, but what is then allowed? What is possible? Okay. Unique constraints. I can specify, for example, after an attribute that it has to be unique. For example, here in the table ape, I have a name and I say it has to be a unique name. I can have referential constraints. For example, I have a second table where I refer to the first table ape via an attribute. I can also do this by the primary key and the foreign key construction, as Wilco explained. So these referential constraints are also a type of constraint, but very specific, just related to references. There is one check constraint that is allowed, and that is a simple check constraint that is only looking at the table itself. So for example, I can have a table and I have a balance. It is a type integer, and I can check if the value of the balance is above 0. And then I have a second attribute called spending without a check. So in this case, the constraint is attached to an attribute in a table, a single attribute. In the second example over here, I attach the constraint to a combination of attributes in the table. So the spending should not be more than the balance I have on my account. So this is possible. It helps a little bit, but not everything. And I saw the generic solution is the writing of your own code, the triggers and the procedures. And it's not so nice. They are not so elegant as the assertions, which you can specify really pleasant. Here, this is more, say, tough programming. However, the good news is some programming environments do support you. And when you specify in OCL these types of constraints, they will generate this code for you. So that's it. One last note, a bit related to the referential integrity constraints, and that is about topology structures or complex features, as they are called in the OGC language or speak. They are not well supported in databases in the sense that they are standardized. Different solutions use different references from the line to the area, or from the line to the line, or from the line to the node, or from the area to the line. Oracle does have support for topology structures, 2D topology structures. For example, is a loop closed if you have a set of edges, which is very important, otherwise you would not have an area. And also an add-on product by Laserscan called Radius is a very good topology solution. And there are also middleware type of solutions where the topology structure is kind of taken care of, not in the database, but in a layer on top of the database. what you could call the layered architecture, in this case for topology structures. And you want to make sure the structure is correct, and that you don't have references that do not exist, that you don't have networks or planar partitions that are invalid. And for example, overlapping crossing edges, overlapping parcels. That is not allowed in a planar partition. You can check it. Okay, I will also fast forward the methodology, so an approach how to specify constraints. I will just summarize it with this slide. First, when you think about the constraint, when you make an information model, say a class diagram, specify in natural words what you think should be the case for your data, and what is not allowed, what is allowed. Okay, it may be informal, it may be vague. Okay, second step is sharpen that expression by using well-defined geometries and topological relationships, as we discussed in these two lectures. The third step is translate that into the right location in your UML diagram and extend that with OCL expressions using the formalization with the simple features and the topology relations. And do some kind of translation, if possible automatic, from that OCL code into the database schema. This is a method which we used in some of our systems we developed with constraints. A road should not cross a building. You see an example that this is natural language. It's obvious. You would not like to have this. But in reality, you can still have this. But this is a kind of subtle trick in the word cross. What does actually cross mean? Here you see the two 3D objects. Say the one is the building and the one could be the space for the road, for the cars. And here you see the 9 intersection matrix. And two objects, A and B, the boundary, the interior, the exterior, and the zeros and the ones indicate, okay, how these two objects are related. So this is a touch. And this is an example of a cross of a surface, the road, and the building, a volumetric object. And there's a difference between this situation, where the surface is really slicing the volume, and here where the surface is not slicing through, but going in a through hole of the building. So it is not really crossing. But if you specify it more sharply what you want, with this kind of topology relationship, the constraint becomes more clear, and this can be checked by a system when somebody starts entering data. Here you see how the OCL is added to the UML class diagrams. Okay, I go to the conclusions, given the time. Okay, OCL is very suitable to specify the constraints. Okay, standard OCL does not have any spatial data types, just numbers and text strings. You can extend it with the spatial data types from the OGC, the simple features. We really implemented this with what we then called pseudo OCL because it has been extended. And we added also in Enterprise Architect, the UML drawing tool, the OCL code. And we would really like that this would be supported by a complete set of 3D functions, 2D and 3D functions. And that when we generate a database schema, the OCL is part of the schema. And to realize this, a lot of automated translation should be realized from OCL to XML in the Exchange, but also to the editor environment, to the front end, QGIS or ArcGIS. You should give visual feedback in the front end and not only give database warnings in the end. And yeah, you should specify once your model with your constraints, and you should reuse that in all the places. In the data storage, in the database, in the data exchange, over the internet, over the web, and in your edit environment. And then the different components will fit to each other at the different parts of your system. Checking constraints can be hard. And I think that is the reason why the database vendors did not implement assertions, because it can be very hard and it can even create kind of deadlocks. So they did not want to have this responsibility. I said, okay, if you want to implement constraints, do it yourself. And this is my explanation why they did not implement this important functionality. Okay, with this, I would like to conclude the lecture of today. It has been a long lecture again. I think you deserve some rest. So enjoy your weekend. I will check the chat right now after the lecture. Respond. I will stop the recording, and I will see you next week after the lecture. So have a good weekend. I hope it was clear why constraints are important, and I hope you understood the importance of well-defined topology relationship based on mathematical principles. Okay.